This is a very good example working in cylindrical coordinates in fluid flow. Let's consider the following case. You have a two-dimensional velocity field, and it's called a line sink. A line sink typically looks something like this, where you can think about this is a source that's actually your fluid is coming radially, purely radial. There's absolutely no rotation in the fluid. So you can, you know that this is equal to 0. The only thing that's non-zero is this. Okay, you only have radial speed. Now, this can be a source if a sink is that goes in the opposite direction. It's negative. Okay, so you're talking about it goes along the z-axis. So it says inboard, outboard here. And then your volume flow rate this is the volume flow rate per unit length of the sink, and this is a negative quantity. Okay, so it's a minus sign there. The first thing we want to do is we want to draw the streamlines of the flow and understand how they look like. Okay, to do that, we're going to do the following. We are going to go ahead and derive the equations for streamlines. So let's get started with that in cylindrical coordinates. So the first question is, can you just find draw the streamlines? Draw the streamlines. We need to actually have the streamlines with us. So if we did that, we know that your vector, this delta S displacement vector, it looks like this. We derived this in class, dz and we know the velocity vector in cylindrical coordinates is equal to e theta plus vz times ez. Okay, so in order to find the stream velocity, to find the streamlines, I'm sorry, you take the cross product this times the velocity vector, and that has to equal to 0. Okay, that's how you find your streams. So if we do that, this is 1 over r, and this gives you ER. This is r d theta. This is in polar coordinates, in cylindrical coordinates, I'm sorry. And then you put the first vector. This is r d theta dz. To put the second vector, vr v theta vz. Okay, and all of this has to equal to 0. So if we do some mathematics here, and so you know this is plus, this is minus, this is plus. So if I start with the first column here, and I say this is plus ER, okay, so this is all going to equal to plus ER, okay, and note that there's 1 over R because of this R. Never forget that. You eliminate this column, this row, you end up with these two terms. It's this term multiplied by this one minus this term multiplied by this one. So we do that, and you can show that this gives you r d theta minus vz, sorry, v theta dz. And then the second term is minus. So you eliminate this column and this row, and you end up this term times this one, this term minus this term times this one. Okay, and don't forget the 1 over r. That's part of the problem. Then you have e theta, sorry, drvz minus vr dz. Then you go to the last term is plus this term, don't forget the 1 over r, Eliminate this row, this column and this row, you end up this times this minus this times this. Okay, so that would give you plus EZ over R V theta dr minus RVR d theta. This is all equal to 0. Okay, now the only way this can actually all of this be 0 is all these terms right here are 0 because each one of the coordinates are completely independent of each other. Okay, so these terms individually have to be 0. Okay, with that said, so we can come here now and we can write those terms. So the first term is R d theta Vz minus V theta dz is equal to 0. And R, then you can simplify this as follows. dz over z. The next term, this one right here, would be dr vz minus vr dz is equal to 0, and that will give you dr over vr is equal to dz over vz. The last term right here is v theta times dr minus RVR d theta is all equal to 0. So that will give you R d theta, V theta is equal to dr over VR. Okay, so these are the three equations that they are equal to each other. So this is equal to this. They're all equal to each other. So in other words, the equations that we get are the following. So you get the following equations. R d theta V theta is equal to dr over VR is equal to d theta bz. Okay, so this is the equations for streamlines. Okay, now in our particular problem, as we just mentioned at the beginning, we show that this, in our problem, this was actually equal to 0, and we are working in the xyz plane. So we can basically say this is not going to be a concern to me. Let's work with these two terms right here. And from those two terms, you can show that you can rewrite those terms as follows. This times dr is equal to r vr d theta. Now, I told you at the beginning, this is a sink, right? Because it's a sink, this is equal to 0. So this is 0. So it will be 0 dr. Okay, so this will be 0. And I'm going to integrate this from 0 to 2 pi. And the integral of 0 just gives you a constant. And that would be 2 pi br times r. Okay, this is not a function of theta. It's independent of theta, so I just get this function in the problem. Now you can also show that this is nothing else than minus your volumetric flow per unit length. And you can check the units here. You can say C is equal to this. And the units are checked as follows. This is L over time. This is L. This is L cubed over time. This is L, will give you L squared over T. So the units are consistent, and I found my C, and I can solve for V. So for a unit source, you can show that VR is actually equal to minus because it's going in the negative direction, 2 pi r L. Okay, so this is the only non-zero velocity that you have. So I can write this in a vector form if I want to. This is minus 2 pi RL ER, and I don't have nothing else. So if you're going to plot this, the plot of this is all strictly along the radial distance, because this is a radial problem. You don't have nothing in the theta. You can have no thetas here. And yeah, and you see that as I approach this to 0, our approach is 0, this goes to infinite. That's okay, but that's just saying, because I have something infinite here, this is a sink. So if I was kind of look from the side, right? If I was just going to try to look from the side and show you what happens, this is the z direction. This was the z direction. So what's really happening with the flow, let me change the colors here quick. What's happening with the flow is saying that it's coming here, it is going to infinite. Okay, there's a sink. That's what it's doing. It's being sucked into a sink. So it happens, just goes to infinite. Okay, that's what he's saying. And that kind of makes sense, right? So your flow is going like this, it's going like this, and it's coming like these are the streamlines of our problem. Okay, so we are done for the first problem. The second question is, what is the volumetric strain rate? Okay, the second problem is, what is the volumetric okay? The volumetric strain rate of your problem is nothing else than you basically find the divergence of B. Okay, the divergence of B is nothing else than your gradient, the dot product of gradient and the velocity. Okay, so we know in the problem, in general, for a cylindrical coordinate, this would be, and we know that this is the only non-zero term that we have in this problem. But let's make this for the general case as a good review. So you can actually do this, okay? And your gradient then is equal to ER partial of V, partial something with respect to R, plus E theta divided by R, partial of, don't forget this R, okay, it's very, very important. That comes from the derivation, the theta, okay? And the volumetric strain, we show that this was actually equal to your volume times dt, or dot times volume, okay? So this is what we are trying to find. So let's just take the dot product of that, and you have to be very careful when you do that. You have to be very careful. You have to handle that with care. So let's go ahead and do the whole derivation step by step, so we don't miss anything. There are many terms that in the cylindrical coordinate, they work beautifully, but when you're working in cylindrical coordinates, in Cartesian coordinates, they work beautifully, but when you're working in cylindrical coordinates, they do not. Okay? So want to work with each one of these cases completely separate and carefully. So let's start with this particular term first. This term is very easy. So this term gives you ER dot product of VR dr will actually give you the following. The derivative of this is, so you're taking the derivative for all this respect to r, okay? So that will be partial of VR respect to R, ER, plus partial of ER respect to R. We have to use the chain rule. Remember that. So, and then now the second term will be partial of B theta respect to theta, E theta, plus partial of E theta respect to theta, B theta. I'm sorry, this is all R, respect to R, respect to R. We are doing this all respect to R. And plus one more term. Partial of Vz respect to R, Ez, plus partial of Ez respect to R, Vz. Now, note, pay close attention. This is not a function of R, so this has to go to 0. In my problem, this is not a function of R as well. This goes to 0. In our problem also, note that this, the derivative of this, will also go away because it's just a unit vector. And we also know in our, if I take this is all I'm left with. I'm left with this term, and this term. So if I take the dot product of all this, the only term that remains non-zero will be the following. VR dr. Okay, so this is the very first term. This is term number 1. Okay, term number 1 is actually equal to this. Okay, this is term number 1. Now let's move on to term number 2. Okay, let's expand on that term. That term will be as follows: E theta r dot partial of v respect to theta. Okay, so what we know is, let's evaluate this term first. Partial of v respect to theta of each one of those terms will be er d theta. And by the way, what I really am doing is, remember, this is equal to, this whole thing is equal to VR ER plus V theta E theta plus VZ times EZ. So what we are really trying to do is we are taking the partial of all this thing respect to theta. That's why I'm using the chain rule. Okay, this will be partial of VR respect to theta, ER, plus partial of E theta respect to theta, V theta, plus partial of V theta respect to theta, E theta, plus partial of Vz respect to theta, Ez, plus partial of Ez respect to theta, Vz. And what we know in the problem, and we showed this in the class, this term is nothing else than E theta. Okay, we know that this term right here is nothing else than minus ER. Okay, and we know that this term right here will be completely equal to 0 because this is not a function of theta, or this is just constant. So if I collect all the terms now, you can show that what you have left is the following: VR plus partial of theta, partial of theta, V theta, partial of theta, E theta, plus VR E theta minus V theta ER, plus partial of V theta, theta, EZ. Okay? So this is what we have in the problem. Now, don't forget that we still need to multiply this whole thing by this term. We had to take the dot product. So what we can do is we take the dot product of this. So I take all this, and I am going to say this is dot E theta over R. And now note that only this term is going to remain. All the other terms are going to cancel out. So basically the second term, okay, term number 2 is going to equal to E theta R, dot product of the theta is going to equal to 1 over R VR plus partial of theta respect to theta. Okay? So now the only term that remains is the last term, and this last term is basically remains the same term itself, right? The term number 3 is nothing else than EZ dot product of this respect to Z. And you can show that the only thing that's going to remain there is VZ respect to Z. Okay, you can show that. So at the end of the day, what you're really left with is this dot product is nothing else, and it's nothing else than the following. 1 over R VR plus, collecting all the terms, okay, you just end up with the following term here. VR partial of V theta respect to theta plus partial of VZ respect to Z. And we can use some mathematical trick here, or if you realize that this is nothing else than the following. If I take 1 over R, okay, then this becomes VR plus R VR respect to R. Or you can further show this is the same thing as dr respect to dr VR. This is 1, right? Plus R VR dr. So in other words, this is the same thing as the partial. This is nothing else a partial of R respect to R VR. Okay? So then this whole thing actually is 1 over R becomes this nice term here, 1 over R, in a closed form solution. So your problem then actually equals to 1 over R BR partial of RVR respect to R plus partial of VZ theta respect to theta plus partial of VZ respect to Z. Okay, this is all the derivation that we do respect this. But now in our problem, is for a sink, this was 0 and your VZ was 0. So this is the only thing that you were left with. Okay, so in your problem, remember this was dot 2 pi L over R ER, right? So this is your VR. This is the only thing that remains non-zero. So in other words, your problem then, this dot this is equal to 1 over R partial of R is equal to 2 pi L R. And if you realize from this particular problem, R and R cancel out here, right? Let me change the colors here. These two cancel out, so this is a constant respect to R that is going to equal to 0. So this is equal to 0. And because this is equal to 0, what this is saying is your volumetric rate is not, strain rate is not changing, so the fluid has to be incompressible. Okay, this is how we put everything together in a nice problem. Okay, so let's go to this last part of the problem. Is the fluid flow rotational or irrotational? Number 3. Is it rotational? Is the question. First of all, just by the problem itself, we know it's not rotational. It's just going inside, right? You have no rotation. It's not doing this. So, but we want to show it mathematically that actually, indeed, you're going to get that equal to 0. The only way this is, so we know that this is rotational only if the cross product of this actually is not equal to 0. If it's equal to 0, then it's irrotational. Okay, so let's see. So we call this the curl or V, by the way, cross V. And in cylindrical coordinates, this is actually equal to the following. R d theta, we already did this previously. Partial of R, partial of theta, partial of Z, VR, RV theta, VZ. Okay, and again we do the same thing, plus, minus, plus, and you can do the whole math. I am not going to go ahead and do the whole math this time around, and you can just show that the curl of V, which is nothing else than your vorticity vector, is equal to, is nothing else, the cross product of this is actually equal to the following term. 1 over R partial of VZ respect to theta minus partial of V theta respect to Z ER plus partial of VR respect to Z minus partial of VZ respect to R E theta plus 1 over R partial of R RV theta minus 1 over R partial of VR respect to theta. This is easy. Okay? So in your particular problem, just recall that your V was equal to this 2 pi LR ER, right? So we don't have any components in Z. These go to 0. This goes to 0. And this goes to 0. The only component I have is in R. This is not a function of Z, so this goes to 0. This is not a function of theta. This goes to 0. So basically, your flow is equal to 0, which if it's equal to 0, it is saying it is irrotational. So your sink is, your flow is not rotating. And you expect that in a sink, right? There's no rotation because I took this away. Now, if you have kept this term right here, you will have seen that you will have come up with some rotation going on here. And there's some interesting values that you could put here that could show that your fluid acts like irrotational. So every single point is not rotating. This point is not rotating. This point is not rotating. Each point in itself is not rotating. That's what it really means. So this concludes example number 3.